Welcome to today's severe weather analysis for Darwin, Northern Territory. This is Thursday, November 27th, 2025. We are analyzing the 9 a.m. local time atmospheric sounding to assess severe weather potential for today and tomorrow. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's start with this morning's sounding at 9 a.m. local time. The basic Skew-T diagram shows our temperature profile in red and dew point in green. Right away, we see a very moist boundary layer with temperature and dew point running close together near the surface at 29 degrees Celsius. Looking at the morning's mixed layer parcel analysis, we have about 760 joules per kilogram of CAPE shown in the red shaded area. That's moderate instability for tropical Darwin conditions. The blue shaded area near the surface shows some convective inhibition, a small lid of about 23 joules per kilogram that's holding things down. The lifting condensation level is quite low at just 457 meters above ground, which is excellent for storm initiation if we can break through that small cap. Deep layer shear from surface to 6 kilometers is relatively weak at just under 3 meters per second, suggesting any storms that form will likely be disorganized pulse-type convection rather than organized supercells. Precipitable water is extremely high at 51 millimeters, typical for the wet season tropics, meaning any storms will be prolific rain producers. Now let's see what happens when the sun heats things up this afternoon. The enhanced multi-parcel Skew-T shows us the transformation. Looking at the heated parcel analysis, we are forecasting a maximum temperature around 33.7 degrees Celsius. When we heat that surface parcel while keeping its moisture content constant, watch what happens to our instability. The surface-based CAPE explodes to over 1600 joules per kilogram, shown in that large pink-shaded area between the parcel path and the environmental temperature. The mixed layer CAPE also increases to around 1346 joules per kilogram. That small blue cap we saw this morning completely evaporates, meaning there's virtually no lid preventing parcels from rising. This is classic tropical wet season setup where solar heating unlocks significant energy. The freezing level remains quite high at 4,900 meters, and our low lifting condensation level of 927 meters means cloud bases will be low with short distance to saturation. However, our deep layer shear remains weak at only 2.3 meters per second, so despite all this fuel building up like a pressure cooker, the lack of wind shear means we won't see organized supercells. Instead, expect explosive pulse thunderstorms with heavy rain and frequent lightning. Looking ahead to tomorrow morning, Friday, November 28th at 9 a.m. local time, the machine learning forecast shows conditions evolving. We're expecting mixed layer CAPE around 891 joules per kilogram and surface-based CAPE of 1122 joules per kilogram. The lifting condensation level rises slightly to 1179 meters above ground. Deep layer shear increases a bit to 3.8 meters per second, but that's still quite weak. Significant tornado parameter remains near zero at 0.01, supercell composite parameter just 0.02, and significant hail parameter 0.17. The storm mode forecast continues to be disorganized convection and pulse storms. Tornado threat remains low, hail threat low, and wind threat low. Essentially, tomorrow morning sets up similarly to today with tropical moisture and instability but insufficient shear for organized severe weather. Moving to tomorrow afternoon, Friday at 3 p.m. local time, the machine learning model shows continued tropical instability. Mixed layer CAPE is forecast around 1346 joules per kilogram, with surface-based CAPE reaching 1717 joules per kilogram. That's substantial fuel for storm development. The lifting condensation level drops back down to 927 meters, perfect for easy initiation. However, the limiting factor remains shear, forecast at only 2.3 meters per second through the deep layer. Significant tornado parameter stays at 0.00, supercell composite also 0.00. The storm mode continues as disorganized convection with pulse-type cells. While tomorrow afternoon will have plenty of energy available, shown by that healthy CAPE, the lack of directional or speed shear in the wind profile means we'll see typical wet season storms, short-lived, intense rain producers with lightning, but not the organized rotating storms that produce significant severe weather. Tornado threat low, hail threat low, wind threat low. The machine learning parameter evolution chart shows us how conditions change through the day. Looking at the CAPE trend line, we see instability starting around 700 to 800 joules per kilogram in the early morning hours, then building steadily through the day as solar heating takes effect, peaking in the mid-afternoon around 1300 to 1700 joules per kilogram before decreasing into the evening. The shear profile remains relatively flat throughout the forecast period, staying in that 2 to 4 meters per second range with no significant increases expected. Storm relative helicity, which measures the corkscrew motion important for supercells, also stays very low throughout the day, never reaching values that would support rotating updrafts. This evolution pattern tells the story of tropical convection, abundant moisture and heating-driven instability, but a benign wind environment. The timing suggests storm activity is most likely in the late afternoon and early evening hours when Cape peaks, but the consistently low shear and helicity values confirm these will be pulse-type cells rather than organized severe storms. The hodograph gives us crucial information about the wind profile and storm motion. Looking at the plot, we see the winds throughout the atmospheric column plotted as we go from the surface outward. The overall shape shows very little curvature or turning with height, which confirms our weak shear environment. The wind vectors are relatively short, indicating light wind speeds throughout the lower and mid-levels of the atmosphere. We can see the bunker storm motion vectors marked with stars. The right-mover supercell motion vector points toward the northeast, which would be the direction any right-moving supercells would travel. However, given our weak shear environment, organized supercells are unlikely. The hodograph lacks the curved, elongated shape we'd need to see for significant storm relative helicity. For comparison, severe supercell environments typically show hodographs with strong curvature and length, creating a banana or semicircle shape. This hodograph is compressed and relatively straight, typical of tropical air masses where convection is driven by instability rather than shear. Any storms that do form will likely move erratically or with the mean wind, producing localized heavy rain and lightning but not organized severe weather. The Brunt-Väisälä frequency profile, or n-squared profile, shows us atmospheric stability at different levels. This plot reveals where the atmosphere resists vertical motion versus where it allows parcels to rise freely. Looking at the profile, we can see areas where the line moves to the right, indicating stable layers that resist rising motion, and areas where it shifts left toward negative values, showing unstable layers where parcels can accelerate upward. Near the surface, we have a relatively unstable layer conducive to initiating convection, which matches what we saw in the Skew-T with easy parcel lifting once the small cap breaks. Through the mid-levels, the profile shows varying stability with some resistant layers that can affect storm structure and longevity. The freezing level around 5 km altitude shows up as a transition in the stability characteristics. This n-squared analysis helps us understand why, even with good surface-based instability, storms may struggle to maintain themselves if they encounter stable layers aloft. For today's setup, the profile supports pulse convection where individual cells rapidly develop, produce heavy rain, then weaken as they encounter resistance, rather than sustained organized systems. In summary, Darwin has classic wet season conditions today and tomorrow: abundant moisture, moderate to strong instability building through solar heating, and very low cloud bases. However, weak wind shear limits severe weather potential to pulse thunderstorms with heavy rain and lightning rather than organized supercells. If storms develop this afternoon, expect brief but intense downpours with dangerous lightning. Always consult the Bureau of Meteorology for official warnings and forecasts, as this analysis provides ingredients only and cannot predict exactly where or when storms will initiate. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia. Stay safe out there.